Next up is a talk by Mark Neu. He's a final year PhD student at the Karlsruhe Institute of Technology. In his research, Mark develops deployment methodologies for machine learning acceleration on FPGAs and heterogeneous system on chip systems. So I'm looking forward to hearing your talk.
Thank you for the kind introduction. Hello, everyone. So the topic of my talk today is microsecond latency, graph neural networks, inference, and point clouds. And before I go into details of the topic, I'd like to give you an overview of the application domain that I work in. So what you see here on the left side is the Belle II experiment of the Super KEK-B facility. This is a particle physics collider experiment in Tsukuba, Japan. It's a E+ E- collider, and it operates at a bunch crossing rate of 250 megahertz. One of the detectors, the one I'll be talking about today, is the Electromagnetic Calorimeter. And this we read out with 8 million detector snapshots per second. So for people not familiar with particle physics specifically, you can imagine this like 8 million frames per second that we need to process. However, our data acquisition system for the full detector is only able to support a continuous readout rate of 30 kilohertz. So we need some online event selection on a real-time hardware trigger. To give you a bit more overview of the experiment, that's how this looks like. You see the electrons, positons colliding in the middle. We call this the interaction point. It's a cylindrical detector, so we have multiple detectors, and the one we talk about today is the electrocalorimeter, which sits just outside of the central drift chamber. Here's another picture of it. It consists of up to 9,000 cesium ionide, thallium-doped cesium ionide crystals. You can see here. So we have the end caps, we have a barrel region, and this is basically our input. You can see event display on the right side. So this is an example. The colored dots here are now crystals, which were hit by a particle or noise. The color gives the energy of the hit crystal. And the goal in our trigger system now is to predict clusters of these energy depositions. You can see also on the right, for example, we have background, but also signal clusters. And this is something we want to deploy for the readout system of this detector. Now, why is this difficult? To give you a quick overview of just how such a real-time trigger system works is, you see this here in the flow. So it's a lot of different systems that are chained to each other to facilitate this readout of this complete detector. And one of the challenges, for example, is we have this 8 million frames per second that we need to process at all times. We have a variable degree of input sparsity in our data that we need to consider. Overall, we have a 5 microsecond latency deadline until the buffer in the first module, the front-end electronics, overflows. And if we deduce all the connections, all the interfaces, like optical connectors, we are ending up with a latency of just 1 microsecond for our algorithm implementation on one of such modules. In addition, we want 100% uptime, so each time our system fails, it stops full detector run, which is quite expensive. So the approach that we use here is a dynamic graph neural network for this calorimeter clustering. We call this Color Cluster Net. We have developed this architecture specifically for this Belle II detector, and it's based on a network architecture called GraphNet, which is a dynamic graph building via k nearest neighbor, and then do a message passing on the learned representation. You can see the algorithm on the right here. As an input, we receive the position of the crystals, the energy and the time, and what we predict is basically the position and energy of a cluster, and we also have a classifier which allows us to differentiate between a signal and a background cluster. The clustering itself is also part of the network and is done with a separate algorithm called the condensation point selection. Now, as you've seen, we need to do this inference in just 1 microsecond. So when we think about what target to deploy this to, we have a large set of different architectures. Typically, you would think of CPUs, GPUs, what everyone uses. However, these are not very suitable because the latency is just too large when we do the inference on them. Recently, we see a lot of neural processing units coming up, like Copilot Plus PCs or similar. They achieve good throughput, but also are not optimized for low latency interface and also not for single event inference necessarily. That's why we usually in this domain work with field programmable gate arrays and or coarse-grained reconfigurable hardware arrays, which basically allow us to map the network as a data flow architecture directly on the hardware. So we kind of build a custom hardware architecture without building a specific ASIC for it. And the question is now, how can we deploy these graph neural networks on these FPGAs at a microsecond scale? For this, we develop our deployment methodology called deploy, which is basically exactly this. So existing works in literature that do this, for example, FIN or HLS form L, exist for simple neural networks, one layer, a few layers, GNNs. We also have some for transformers, but so far there's not really support for graph neural networks or point cloud networks in general. What we give in our tool is basically domain-specific optimizations for these low latency, high throughput inference in particle physics. Well, basically the flow you can see on the right, so I'm not going into detail, but as a user, what you give us is like an ONNX model and some system requirements, and what the tool generates is a hardware description of the accelerator, basically. On the back end here, we use a commercial tool, which is AMD tool for high-level synthesis, which does the algorithm conversion into actual hardware. Just to give you a quick idea, how does this look like? So in general, our point layer looks something like this. We have a message passing step, we have a graph building step. First, we decompose this into the message passing into scatter, transform, aggregate, something like this, and the graph building into an all nearest neighbor calculation and the filtering. So for example, this can be top K for a K nearest neighbor algorithm. Now, skipping some details, basically, we use these operators that we have now, and we map these in some way on the on hardware. So each algorithmic operator now gets to be a processing element on the hardware platform. You can see this, for example, for the GraphNet as an example on the bottom. And yeah, with this concept now, I want to present you some results that we have. So we've developed we call this the GNN ETM. You can see it on the right. Our team is up there installing it in the Belle II detector, actually. In general, this system facilitates the inference of this graph neural network on the electrocalorimeter that you've seen before. We have multiple latency critical stages, so we do all the pre-processing in hardware, then we do the inference of the network, basically in the middle, and then in the end we have some post-processing of it. All this is done on AMD ultra-scale FPGA on our trigger board, and of course we can also read out some debug data. Yeah, the network that we deploy here, so you can see the GraphNet layer basically in the middle here, is this. So in this case, it's a very compressed network because we need to achieve this 1 microsecond. What you see here is basically 15 layers roundabout. It's fixed point quantized, of course, to make it smaller on the FPGA. And with this, after some optimization, actually an implementation, we achieve a final latency of just above 1 microsecond. So the full design runs at 250 megahertz on the FPGA. We achieve 8 million detector snapshots that we require per second that we can compute. And this system is also included in the Belle II first level trigger system since now over a year. And we continue to take monitoring data to debug the system further. So now to conclude my talk, so we have developed a template-based deployment approach for graph neural networks on FPGAs. These hardware templates are also available in our open source kernel library. We've designed and implemented a GNN-based clustering algorithm for the Belle II ECL trigger. This is the first GNN-based reconstruction algorithm running in a real-time environment at a particle physics experiment. And we have optimized the GNN ETM to actually achieve this just above 1 microsecond end-to-end latency, and commissioned the system inside the particle physics experiment, validating it. And just as a last advertisement slide, so we try to make this now a bit more diverse for other experiments in the DEEP project. So if you have similar problems or something, I'm happy here to talk with you about this. Thank you for your attention, and I'm open for questions.
Yeah, thanks a lot for the nice talk. We have time for one question. Fabian.
Thanks, impressive. Congrats that you were able to actually sort of really convert a complex, potentially sort of not maybe somewhat stochastic algorithm to really fixed boundary. How do you make sure that, due to whatever configurations and so on, you don't exceed your time budget and you still sort of deliver something? Because it could be there's due to stochasticity or something.
Basically, what we do is we convert this dynamic sized input into a statically sized input by some kind of padding. So we make sure that the input has a maximum input size. And then we do some called static scheduling. So basically, all the tensor bounds that we calculate basically are static. So we can guarantee by design that our system will always achieve the same latency in this pipeline. And then because we do not have any CPU inference, we also don't have any non-real-time.
Is this specific for the FPGA type of setup that you have, or do you think are there also sort of known bounds that we can give to any of our deep learning algorithms? I'm not sure. Like if I implement something in CUDA, so I don't know if I can give this bound, right?
In general, this is a huge, I would say, real-time computing is a big field. So it's a bit hard to say this, but I think most research focus on how to make software systems with real-time bound, with worst-case execution time. We circumvent this full problem by just avoiding software altogether and by basically putting it into hardware. And this way we circumvent all this. If you want to do this on a CPU, I think CPU is more feasible, but you run into caching problems. GPU is a bit more difficult with PCI Express and stuff like this. Yeah, I think we're running out of time, but happy to discuss further.
Yeah, thanks a lot.
Thank you.
Let's thank Mark again.